Here is another little video about Le Chatelier's principle. And a reminder, Le Chatelier's principle states that when a system at equilibrium is exposed to a change, it will shift in a direction that partially opposes that change. We do this to try and maximize the yield from a chemical system. Here we're going to look at what happens when we increase the temperature. Now obviously, increasing the temperature is the opposite of decreasing the temperature. So while looking at what we can do when we increase temperature, you can just think about the opposite will happen when we decrease temperature. So what happens, according to Le Chatelier's principle, when we increase the temperature of a system? Well, Le Chatelier's principle states that we need to decrease the temperature somehow because we need to partially oppose the change that's made to our system. So when we increase the temperature of our system, what's going to happen? The reaction is going to favour our endothermic direction, whichever that may be. It might be the Ford's reaction, it might be the reverse reaction. But the key thing is, if I increase temperature, it will favour the endothermic reaction. So like we did last time, let's try and explain this with reference to collision theory. And that's about the rates of reaction, because at equilibrium, rate of forward and reverse reaction are equal, but if we push a change on our system, that means the rates become not equal, and we need to be able to understand why that might be the case. So, what happens when we increase temperature in terms of collision theory? Well, the rate of both the forward and the reverse reaction both spike. The reason? Because we have a greater proportion of particles with the activation energy. So therefore you can see on the graph here, when I increase temperature right about here, both the forward and reverse reaction spiked. But an interesting thing here is you can see that one of these rates spiked more than the other one because that direction was favored. Whichever rate spikes more, that must be our endothermic reaction because it has to be going faster than the exothermic reaction. The graph I've got here shows the Ford's reaction being favored a lot faster. That is not always going to be the case, but in this case, it means that the Ford reaction was endothermic. So you can't always say the Ford's reaction is going to be favored. It depends on the delta H and the enthalpy of reaction. If you're increasing the temperature, you always favor the endothermic reaction, whether that's forward or reverse. Hopefully this helps you understand about the rates of reaction in terms of equilibrium and also Le Chatelier's principle in terms of a temperature change. Next up, we're going to look at how concentration, volume, and pressure are all linked and how these can be used as a factor to maximize yield as well.